Hello everyone, welcome to my channel Abhilash2021. If you are new to my channel, then please listen to the end of the video. If you like my explanation, then subscribe to my channel and share with your friends. Now let us jump into our topic, real numbers. In this video, we are going to discuss exercise 1.1 of the chapter real numbers. The first question is, use Euclid's division algorithm to find the HCF of 135 and 225. First, the given two numbers do division. 135 and 225. 135 ones are 135. Do subtraction of this. 5 minus 5 0. 22 minus 13 9. 90 is the remainder. Now this we need to write it as dividend equals to divisor into quotient plus remainder. So here the dividend is 225. 225 equals to divisor into quotient 135 into 1 plus remainder. This is only in 10th class we will read it as A equals to BQ plus R. In our terms, dividend equals to divisor into quotient plus remainder. Now from this step we need to pick our divisor and remainder, and again these two numbers we need to do division. So for 90 and 135, if you do division, 90 ones are 90. 5 minus 0 5, 13 minus 9 4, so the remainder is 45. Again for this if we write dividend 135 equals to divisor into quotient 90 into 1 plus remainder 45. So now again from this step we need to pick the divisor as well as remainder. We need to do division of those two numbers again. So 45 and 90, if you do division, 45 2s are 90. 90 minus 90 is 0. So let us write this also in the form of A equals to BQ plus R, or else a dividend equals to divisor into quotient plus remainder. 90 equals to 45 into 2 plus 0 remainder as it is. So whenever if we get the 0 as the remainder, then we need to stop the process there. So after getting the 0 remainder, then we need to check the what is the divisor here. In this case the divisor is 45. So our HCF is 45. So the HCF of 135 and 225 is 45. Now without wasting the time, let's move to the second question. 196 and 38,220. Of course here the number is a little bigger, but there is no need of worrying about that one. The process is as it is again. So let us do the division of those two numbers. 196 38,220. So first if we observe, in this first digit is 3. 196 table 3 won't come. Then 2 digits 38. 196 table 38 won't come. Then 382. So 382 or else near to 382 will come in 196 table. So we need to solve that first. So 3 digits we need to solve at a time. That is 196 ones are 196. From 2 we cannot subtract 7. So this 2 will become 12, this 8 will become 7. 12 minus 6, it is 6. 7 minus 9, again from 7 we cannot subtract 9. So again we will take borrow, then this 7 will become 17 and 3 becomes 12. 17 minus 9, 8. 2 minus 1, 1. Now 196 is the divisor. In 196 table 186 won't come, so I need to drop one more digit down, that is 2. Now 1862. 196 tenza is 1960, but here 1862 is there, so that is smaller than 1960. So that's why I am directly checking with 196 9za. 196 times 9za, that is 96 54, 4 5 carry, 9 81, 86, 68 carry, 1764. So 196 9za 1764. Now again 196 table, sorry, let us do subtraction first. Here from 2 4 want to go, so this 2 we will take it as 12 and this previous 6 will become 5. 12 minus 4 8, 5 minus 6, again it's not possible, so again I need to take borrow, so that this 5 will become 15 and the previous digit 7 it will become 7. So 15 minus 6 9, so the answer is 98, and here 196 table 98 won't come, so drop the last digit also, that is 0. 980. Now we need to check in 196 table where we will get 980 or at least near to 180. So here if you observe clearly, this is 6, this is 0. So in 6 table where we will get the last digit as 0. So that is possibility with a 5 because 5 6 are 30, right? So the last digit is 0. So I am trying to check with the directly 5 table. 196 5 5 6 30, 0 3 carry, 5 9 45 48, 8 4 carry, 5 1 5 9, 980. So we got it as 196 5 980. 980 minus 980 is 0. That is the remainder. So now what we need to do is, let us write this in the form of A equals to BQ plus R. Here dividend is 38,220, that is equals to divisor into quotient 196 into 195 plus 0 is the remainder. So here in the first step itself we got the 0 as the remainder, so process completed, then there is no need of doing further. So after getting the 0 remainder we need to check our divisor. Here the divisor is 196, so the HCF is 196. Let us move to the third question. 867 and 255. Let's do the division of these two numbers. 867. Now 255 1 is 255, so 255 2 is a little bigger, 510, and so I am checking with 255 3 then. Let us hope for the best. 255 3 3 5 15, 5 1 carry, 3 5 15 16, 6 1 carry, 3 2 6 7. Okay, it's near to 765. So 255 3 765. Let us do subtraction of these two numbers now. 7 minus 5 2, 6 minus 6 0, 8 minus 7 1. Now this we need to write it as the step. Dividend 867 equals to divisor into quotient 255 into 3 plus remainder 102. Now from this step we need to pick the divisor as well as the remainder, and we need to do division again for those two numbers. So 102 and 255. 102 is 204. So 5 minus 4 1, 5 as it is. So we will get it as 255 equals to 102 2s plus remainder 51. Again from this we need to pick the remainder and the divisor. We need to do the division of these two numbers again. So 51 and 102. 51 2s 102. So we will get the remainder as 0. So our final answer will be 102 equals to, that is dividend equals to divisor into quotient 51 into 2 plus remainder 0. So here the remainder we got it as 0, so we need to stop the process here, and in this case we need to find out the divisor. So the divisor is 51, then our HCF is also 51. Let's move to the bit number 2. Show that any positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Now observe this given question clearly. 6q plus 1, 6q plus 3, 6q plus 5. These all three numbers are in the form of a equals to bq plus r, right? So just forget about this a equals to. So now these all three numbers are in the form of bq plus r. So here before the q we have number b, right? That is nothing but divisor. So in this question also, before q we have 6, here also 6, so here also 6. So from the question itself we can confirm that b, that is divisor, is given as 6. So in the next while solving the problem, wherever it is necessary, I will use that one. So what the sentences we need to write for this kind of question is, let a be any positive integer, any positive integer, and b equals to, b is nothing but divisor, right? So here the divisor is digit 6, so b equals to 6. Then by Euclid's algorithm, what is our Euclid's division algorithm says? A equals to bq plus r, right? So now a is some integer we took already in the first line itself, so that's why I'm keeping that a as it is, equals to b value, I know it as 6, right? So b I am replacing with 6, q plus remainder as it is. For some integer, q, that is greater than or equals to 0. And now here the divisor is a 6, right? So if the divisor is a 6, then what are the possible reminders? So always the remainder starts from 0 onwards. 0, 1, 2, 3, then till where we need to write, that will be depended by the, again, divisor only. Remainder always starts from the 0 and it should be less than the divisor. Here in this question divisor is 6, right? So the reminders will come till 5, less than 6, that's it. Now what we need to do is, these reminders one by one we need to substitute in the formula. Our Euclid's division formula is a equals to bq plus r. So a is some unknown number, keep it like that only, equals to b value we know as 6, right? In the question itself, so 6q plus reminders, one by one reminder I am substituting now. So first 0 reminder, that is nothing but 6q plus 0 is 6q simply. Next a equals to 6q plus next reminder 1, then a equals to 6q plus next reminder 2, then a equals to 6q plus 3, then comes a equals to 6q plus 4, then finally a equals to 6q plus 5. Next, what exactly is asking in the question then? Show that every odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Okay, let us check these answers, whatever he got. Here, there is no remainder at all. So, we can say that it is an even number. Here, plus 1 is the remainder. So, this is odd number. Plus 2 is the remainder. This is even number. Plus 3 is the remainder. This comes under odd number. Plus 4 is the remainder, this is even number. Plus 5 is the odd number. So now if we observe this, wherever we got the odd numbers, let us concentrate only on that part now. This is odd 6q plus 1, this is odd 6q plus 3, this is odd 6q plus 5. So now we can decide that therefore any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Let's check the question number 3 now. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. Then what is the maximum number of columns in which they can march? In this kind of questions, the logic is very simple. we will get always a doubt whether we need to use LCM concept or else HCF concept. So whenever if you do HCF, always the number is equal to the given numbers in the question, or else it will be smaller than the given numbers. Next, if you do LCM, always the number is equal to the given one of the numbers, or else it should be bigger than both the numbers. Now forget about this equal in both the two. So just remember that if you do HCF, you are going to get a smaller number. If you do LCM, you are going to get the bigger number than which is given in the question itself. Now we need to divide some members into groups or else columns. Then it is impossible to have more numbers than the given one. For example, in this question 616 people are there. So 616 members, if I arrange in any way also, I won't get more than 616 people. That's impossible case. So definitely I have only one number, that is compulsory HCF only. Because 616 members, if I arrange in some groups or else some parts, then definitely the number of people in that group or column should be definitely smaller than the 616 members as well as 32 members only. Definitely, then only that case is possible. So now we need to find out the HCF of these two numbers. So already we know how to find out HCF by Euclid's division. So let us do that one then. HCF of the given two numbers 616 and 32. So as usual, first division 32 and 616. 32 2s are 64, so not possible. So just 1s are 32, 1s are 32. 11 minus 2 9, 5 minus 3 2, 29. In 32 table 29 won't come anyway, so we need to draw one more digit also, that is 6. So 32 and 296 we got. So in 32 table where we will get 296. 32 tens are is 320, so 9s I will check then. So 32 9s are 9 2s are 18, 8 1 carry, 9 3 27 28. Okay, that's it. So 32 9s are 288. 288. If you do subtraction of this one, 296 minus 288 is 8. So now let us write this in the form of dividend equals to divisor into quotient plus remainder. 616, that is dividend, equals to divisor into quotient, that is 32 into 19 plus remainder 8. Now from this step again we need to pick the divisor as well as remainder. In this case the divisor is 32 and the remainder is 8. So here no need of any long division because I know 8 table perfectly. So 32 equals to 8 4s are 32 plus 0 as it is. So whenever we'll get the 0 as the remainder, then we will stop the process there itself. So here 0 we got, then 8 is the HCF. So HCF of given numbers, I mean 616 and 32 is 8. So it means the maximum number of columns is 8. Move to the next question. Use Euclid's division lemma to show that the square of any positive integer is of the form 3m or 3m plus 1 for some integer m. Now the previous also we did one question like this, just the same like that only. Let a be any positive integer, and b equals to, b is nothing but divisor, right? So that will be in the question itself. 3m plus 1 3, so that number 3 is the divisor, so the b value is 3. Let a be any positive integer and b equals to 3. So by Euclid's division algorithm, Euclid's division algorithm, or simply we can write Euclid's division also. That is A equals to B cube plus R, right? So now A is as usual equals to B value 3 Q plus R. Now here what are the possible reminders then? R equals to, the divisor is given as 3, right? So then the remainder should be starting from 0 and less than 3. So 0, 1, 2. Now this remainder, let us substitute in the formula. A equals to 3Q plus R is our Euclid's division algorithm, right? So A equals to 3Q plus first remainder 0. So A equals to 3Q plus 0, 3Q. This is what exactly we did in the previous question also. But in the question here he is asking something different. That is, use Euclid's division lemma to show that square of any number. In the previous question he didn't mention the word square, but here he is mentioning the square. So that's why we will do squaring on both the sides. Squaring on both the sides. So A equals to 3Q is there, right? So for that do squaring on both the sides. A square equals to 3Q whole square. So we will get A square equals to 3Q whole square. 3 3s are 9, Q square as it is. So we cannot simplify further because we don't know the value of A as well as we don't know the Q value of Q. So A square equals to 9Q square. Now what we can able to do here? Check clearly. A square as it is equals to, here in the question he is asking to show that it is in the form of 3m plus 1, right? So the 3 is common, right? So that's why here also take 3 as common. Now what will remains then? 3Q square. 3 3s are 9, Q square. So A square equals to 3 into 3Q square. It is in the form of, 3m. So here m is nothing but this 3Q square. Next, let us take the second remainder, that is 1. A equals to 3Q plus next remainder is 1. Again for this also doing squaring on both the sides. A square equals to 3Q plus 1 whole square. Left side we don't have any work with that, so just leave it like that only, equals to. Now right side part if you observe, 3Q plus 1 whole square. That 3Q plus 1 whole square is in the form of A plus B whole square. So if we expand that, A square plus B square plus 2 into A into B, that is equals to 3Q whole square 9Q square plus 1 square 1 plus 2 into 3Q 6Q. So here I took 3 common, right? So here also I am going to take 3 as the common. Then if we take 3 common, 3 3s are 9, so 3Q square plus 3 2s are 6, so 6Q. Now in 3 table 1 won't come, right? So that's why I am writing that 1 separately completely. So that is the reason I wrote the 1 at the ending. Now if we observe this one, it is in the form of 3, this is some alphabet plus 1. That alphabet is nothing but M. So it is in the form of 3m plus 1. Now 0 remainder completed, 1 remainder completed, then the next one is 2 remainder. So let us substitute with 2 remainder now. A equals to 3Q plus 2 is the remainder now. Same as usual doing squaring on both the sides. So what we get, A square equals to 3Q plus 2 whole square, which is equals to 3Q plus 2 whole square. It is in the form of A plus B whole square, right? So if we expand that, we will get 3Q whole square plus 2 square plus 2 into 3Q into 2. A square plus B square plus 2AB, which is equals to 3Q whole square 9Q square plus 2 square 4 plus 2 3s are 6, 6 2s are 12, 12Q. Now we need to know a small logic here, that is here the remainder is 4, right? But in 3 table otherwise the divisor is 3. So always the remainder should be smaller than the divisor only, but here the remainder 4 is bigger than the divisor 3, so it is not possible. So that is the reason we will separate that 4 as 3 plus 1, divisor plus 1 plus 12q as it is. Now again keep that 1 completely to the dead end, 9q square plus 3 plus 12q plus 1 aside again. Now from these 3 terms we can take out 3 common. So if we take out 3 common, then 3 3s are 9q square plus 3 1s are 3 plus 3 4s are 12q as it is plus 1 again as it is. Now again it is in the form of 3m plus 1, where m equals to, here what is there inside of the bracket. Now coming to the question number 5. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. First case he did not ask about anything of square cubes. In the second case he asked about the cube. Now he is speaking something related to cubes. So if anyone don't know the cube formula means, please make it a note of it. A plus b whole cube equals to a cube plus b cube plus 3a square b plus 3ab square. Okay, now let us check the statements as usual. Let a be any positive integer and b equals to, now in the question he is clearly mentioned that 9m plus 1, 9m plus 8, right? B, if we take as the 9, it takes a lot of time to solve them, because if 9 is the divisor, then the remainders will be 0, 1, 2, 3, 4, 5, 6, 7, 8. Those many times if we need to do problem, and that too for cube means it takes a lot of time. So we need to check for some alternative, that one. That is, instead of taking the b value as 9, I will replace that b with a 3. Why? It means if 3 is the divisor, then the possible remainders are 0, 1, 2, right? 0 square 0, it satisfies the first one. 1 square 1, it satisfies, 1 cube 1, it satisfies the second condition. 2 cube 8, it satisfies the third condition also. That's why I am writing the b value as a 3 instead of 9. So now by Euclid's division, a equals to bq plus r. Let us substitute in this now, 1 by 1 neatly. A equals to b value is 3 q plus r. Then what are the possible remainders here? Remainder equals to b value 3, right? So 0, 1 and 2. So let us substitute 1 by 1 remainder now. A equals to 3q plus 0 remainder. A equals to 3q plus 0, simply 3q. Now in the given question he said that cube, right? So do cubing on both the sides. Cubing on both the sides. So we will get a cube equals to 3q whole cube, that is equals to 3 cube 27 q cube. Now as the divisor is 3 again, as well as he is saying that it should be in the form of 9 only, right? So that's why I am not going with the divisor. Whatever is given in the question, that 9 number, that's why I am taking 9 only as common here. So we will get 9 3s are 27 q cube as it is. Now it is in the form of 9m. Next, let us take the second remainder then. A equals to bq plus r is the Euclid's division. A equals to b value is 3, q as it is, plus the remainder is 1. Now again cubing on both the sides. A cube equals to 3q plus 1 whole power 3. left side a cube as it is equals to 3 cube plus 1 whole cube. Now the 3 cube plus 1 whole cube is in the form of a plus b whole cube, right? So a plus b whole cube formula is a cube plus b cube plus 3a square b plus 3ab square. So a cube plus b cube plus 3 into a square into b plus 3a b square. That's it. Now let us simplify this further. 3q whole cube, 3 cube 27, so 27 whole cube plus 1 cube 1 plus 3 as it is. Here for 3q square is there, right? So let us simplify that first. 3 square is 9q square, 1 as it is plus 3 into 3q into 1 square 1, which is equals to 27q cube plus 1 plus 3 9s are 27q square into 1, anyway not necessary, plus 3 3s are 9q into 1 is 9q again. Now again I will write the number 1 at the ending completely. So we will get that as 27q cube plus 27q square plus 9q plus 1. Again from the first, second, third terms I will take out 9 common. So 9 3s are 27q cube plus 9 3s are 27q square as it is plus 9 1s are 9q as it is, and finally plus 1 again as usual. So now it is in the form of 9m plus 1, where m equals to which is there in the bracket. So 0 remainder completed, 1 remainder completed. Now let us move to the 2 as a remainder. A equals to b cube plus r. A equals to b value, we took it as a 3, q plus remainder is 2. Cubing on both the sides. A cube equals to 3q plus 2 whole cube, which is equals to, now 3q plus 2 whole cube is in the form of a plus b whole cube. So if we expand that, 3q whole cube plus 2 cube plus 3 into 3q square into 2 plus 3 into 3q into 2 square, which is equals to 3q whole cube, 3 cube is 27, q cube as it is, plus 2 cube 8 plus 3 into 3q whole square 9q square into 2 plus 3 into 3q into 2 square is 4, which is equals to 27q cube as it is plus 8 as it is plus 3 9s are 27, 27 2s are 54 q square plus 3 3s are 9, 9 4s are 36 q as it is. Now again this 8 I will keep it last, 27 9 cube plus 54 q square plus 36 q plus 8 as it is again. Now from the first, second and third terms I will take out 9 common. So we will remains with 9 3s are 27 q cube as it is plus 9 6s are 54 q square as it is plus 9 4s are 36 q as it is plus 8 final again at the dead end only. So now it is in the form of 9m plus 8, where m equals to what is there in the bracket, that total we need to write, 3q cube plus 6q square plus 4q.